On day one of a computer science degree, the most terrifying object in the room is the blinking cursor. Students arrive expecting to write raw code, and the sheer volume of syntax they don't know instantly paralyzes them. But in this specific course, they aren't students. They are immediately onboarded as creators at a fictional tech conglomerate called AlgoCratic Futures. They don't get grades. They get assigned to the lowest possible security tier, infrared clearance. At infrared, their agency is completely stripped away. They are assigned a platform AI agent named Shodan, a dedicated success partner who locks them out of writing custom prompts entirely. They are restricted to rigid, fill-in-the-blank execution wizards. This constraint serves a precise pedagogical purpose. If novices have access to an AI on day one, they will guess its syntax until something compiles. By stripping away their ability to generate code, the curriculum forces them to understand the structure of the work before they ever attempt to build it. Before they touch a single line of Python, their first hurdle is figuring out what to build. They are handed the manual for a 1977 math toy called Dataman and told to modernize it. To do that, they have to read the legacy document like an analyst. They pull out two specific things: features, which are the distinct capabilities the manual promises, and user roles, identifying exactly who the machine assumes is operating it. The climax of week one arrives when the students synthesize those findings, open their version control environment, and make their very first git commit to their public repository, known here as their channel. The moment that commit lands, the platform rewards them with its bizarre metric of success, exposure units, or XU. They accrue this fictional currency automatically, simply for participating in the workflow, regardless of whether their initial analysis is actually any good. Establishing the habit of shipping a bad, highly visible commit provides a foundation for iteration that a perfect, invisible idea never can. Moving into week two, the students complete their debut stream and unlock red clearance. Now they have to take the raw facts they extracted from the manual and translate them into actionable engineering tasks. This illustrates the strict syntax they must adopt: the agile user story. Every request is structured as a specific role, I want to perform an action, to receive a specific value. Ambiguous needs filter through these variables into a compact, schedulable package of work. But a story isn't done until you can prove it works. They must write acceptance criteria, strict binary conditions that determine whether the task was genuinely completed or if it failed. When a student inevitably hits a roadblock and a test fails, the AI agent doesn't write the fix. Instead, Shodan triggers the FIGURE debugging protocol. It forces the student to isolate the exact line number and expected output, shrinking the problem down rather than rescuing them from it. This separates the mechanics from the intent. A generative model can spit out Python syntax all day, but only the human has the necessary context to define the acceptance criteria that dictate what the code is actually supposed to do. By week three, the stakes rise. A plain text list of user stories is invisible to the scheduling algorithm. Work cannot be planned until it carries a specific cost. The students are tasked with assigning story points to every item in their backlog, estimating the true cost of their proposed software build. This chart shows the required estimation scale, the modified Fibonacci sequence: 1, 2, 3, 5, 8, 13. Notice the exponential leap as values increase. Those higher numbers are alarm bells, flagging tasks dangerously complex that must be broken down before anyone writes code. The immediate trap students fall into is attempting to map these abstract points directly to hours on a clock. They have to break that instinct. Points measure complexity and effort, not time. Once the board is costed, the algorithm enforces a brutal limit. They only have 13 points of capacity for the entire sprint. Using the Moscow prioritization method, must have, should have, could have, won't have, they are forced to ruthlessly cut features until their math fits the capacity constraint. Estimating and cutting backlog items forces a complete shift in perspective. They have to abandon the mindset of a hobbyist working with infinite time and adopt the mindset of a business owner managing strictly finite resources. Step back from the weekly timeline and the overarching architecture of this environment becomes clear. There is a deeply intentional three-layer model dictating their reality. The curriculum operates through a specific structural geometry. The core is layer 0, the actual student, encased within layer 2, the fictional corporate environment where the developer persona operates. When a build breaks or a sprint fails, the damage hits that fictional layer. Instead of a grade penalty, a failure suffered by the character is recorded as valuable content at layer 1, the platform. The absurd corporate demands and exposure units act as a protective buffer. Learning to engineer software in public is an intensely vulnerable experience. This system intercepts that vulnerability and reroutes it into a structured, gamified process. The dystopian roleplay functions as psychological armor, allowing students to build resilience by distancing their personal identity from their technical failures. At the end of week 3, the students are staring at prioritized, estimated, and fully costed Kanban boards. They have a documented plan. They have reached the threshold of prompt sovereignty. The guided wizards and safety protocols vanish, granting them direct, unmediated control over the AI interface. At this point, they haven't coded a single full application, but they have mastered problem definition, environment setup, and constraint management. In a landscape where artificial intelligence can instantly generate thousands of lines of syntax, the ultimate engineering skill is no longer typing. It is the ability to confidently translate human ambiguity into precise logic that a machine can safely execute.